Hi, this is Mr. Adams, and this is a video on some basic gas laws. We did the combined gas law in class. Okay, it's on your reference table, and we discussed the fact that these ones right here mean the initial or old conditions, and the twos represent your final or new conditions. All right. When using the combined gas law, what you want to do first is cross multiply to make your life simple. So in essence, you will cross multiply the t's. This t1 would go over here. This t2 would go over here, resulting in p1 v1 t2 equals to p2 v2 t1. Okay, and then you isolate whichever variable you need to find by dividing by the other two. So for example, if you're trying to find v1, you would take p1 and t2, divide both sides, and you'll go from there. But we'll do an example later on. Okay, another important thing we need to know is that if we're working with temperature, we must use Kelvin temperature. Okay, so if we're given degree C, please change it to Kelvin. All right, it's very important. And also, we have some other laws that we work with where we'll find some variables will be constant. If those variables are constant, we will make them 1. Okay, so we'll do an example with it also to see what we're talking about. Okay. Boyles Law. Boyles Law is a condition, and Robert Boyle did some experiments where he held temperature constant, right? So he was considering pressure and volume. And it was found that pressure and volume have a inverse and proportional relationship. Inverse in the sense that as one thing goes up, if I increase pressure, my volume gets decreased. If I decrease the pressure, my volume gets increased. Okay, so as one goes up, the other guy goes down. And as we just said before, if one of the variables is constant, okay, we will turn it into a 1, and this is what we mean. Since temperature is constant in this case, we will turn these temperatures to 1, okay? So we have now P1 V1 equals to P2 V2. Now the nice thing about this is that you can use the combined gas law to solve any of these problems. Even if you forgot the name of the particular scientist, you simply use the fact that whatever's constant, I'm going to turn it into a 1, and I'm going to get my answer from there. The general shape of the Boyles Law relationship between pressure and volume is this curve right here, so you should know that. And it has life implications in terms of, for example, with deep sea diving with pressure and volume. As you go down into deeper depths in the sea, your lungs actually get contracted. And for example, if you come up from that depth and you don't equalize the pressure, come up carefully, okay, you can cause seriously bodily harm to yourself. Okay, so that has life implications. All right, Charkes Law. Now Charkes Law is a little similar to Boyles Law. There's something constant, but what's constant in Charkes Law is pressure. Okay, so pressure is constant. So what we're going to do, we'll use our combined gas law again. We're going to turn the pressures to 1. All right, and we wind up with this equation over here: V1 over T1 equals to V2 over T2. Now, once again, as we discussed in class, we don't panic. It looks kind of weird, but whatever you do, we just simply cross multiply first. All right, so we cross multiply, and what we wind up with is V1 T2 equals to V2 T1, and we go from there in terms of calculations. All right, cross multiply, then you isolate. Now what happens in Charkes Law, if we have a lower temperature and we increase it, we increase the average kinetic energy of the particles of gas, the volume will also increase. Or on the flip side, if we have a gases at room temperature in a balloon, for example, and we lower it by adding liquid nitrogen, okay, lower temperature, lower average kinetic energy, the volume will also decrease. So we see that in Charkes Law, the relationship is direct and proportional, okay? And the graph will look like this, a direct and proportional relationship in terms of Charkes Law. All right. And we didn't do this law in class, but it's similar to the rest. There's something constant once again, But what's constant in this law is volume. Now this law is called the Lussac law. All right, and volume is constant. So what we're gonna do, we'll change the volumes to 1. Okay, and we wind up with this guy right here. This equation, P1 over P2 equals to T1 over T2. As before, we cross multiply if we want to use it. So we get P1 T2. Okay, that cross multiplies over there, equals to T1 P2. All right, this cross multiplies over there. And whatever variable we need, we don't panic, we just isolate it and divide by both sides by the other one. Okay, now in terms of this Lussac law, right, at constant volume, it also has life implications. We increase the temperature, right? The average kinetic energy will also increase, right? And since we have constant volume, all right, the molecules or particles are smacking into the walls of the container at a greater rate and a faster rate, increasing the pressure. Now, you've seen on aerosol cans, I'm sure, keep away from flame, not just because of the flammability, but also because of this law. If you have these particles smashing around more and more and the temperature gets higher, what eventually can happen, you can create basically a bomb situation, and that's not good. So be very careful with aerosol cans and heat. All right. Once again, a relationship between temperature and pressure at constant volume is also direct and proportional, as we see in this graph right here. If we extrapolate it down, you get close to absolute zero. Okay, now what we're going to do right now, you will pause the video, you will do this problem right here, okay, number 22. You'll pause the video again, you'll do number 4, okay, right here, and you pause the video again and do number 7. Okay. Now for number 22, we have our combined gas law. You can always start with that, and we look at this problem. Okay, so we're looking at it. We have an unopened cold soda can of 2 liters, soda bottle, and it contains, okay, it contains eventually a 4-liter reaction vessel. So what's going to happen is, guys, let's start again. We're going from a 0.005 liter container, all right, and we're going to get it to, oh boy, all right, let's try again. We have a 2-liter soda can with 46 mLs of gas in it. I switched my page by mistake, not a problem. All right, so what you do, guys, you put your information on the side first. You got P1, V1, T1, and we have P2, V2, and T2. All right, you put your information on this side. Now we see 46 mLs right here, so that's going to be our V1, our 46.0 mLs of gas. All right. Now this 2 liters right here, we have to be careful. That's not our gas volume. This right here is our gas volume. That's the volume of the soda can. So we don't really need that. All right. It's extra information. Now it's confined at 1.30 atmospheres. So atmospheres is pressure. So it's 1.30 atmospheres goes right there. Alrighty. And the T1 is 5 degrees. So we can put 5.0 degrees C right there. All right. Okay. Now the thing is, guys, word of warning, we cannot use degree C, so we will add 273 in our chart right there, right away. Okay, so 273 plus 5 should be 278 Kelvin. So if you're making your chart on the side, change to Kelvin right away so you don't forget. All right, so those are our initial conditions. They take the bottle, they drop it into a lake, all right, with a pressure now of 2.85. So your second pressure, your final pressure is going to be 2.85 atmospheres. Alrighty? Okay? And the temperature of the lake is equal to, right here, is 2.09 degrees C, right? So what we're going to do, we're going to convert that to Kelvin. So you get 273 plus 2.09, so that should give you what? That should give you 275.09. Okay? Alrighty. So that's our Kelvin temperature. Now we are trying to find the volume of gas in the bottle. So that will get you a question mark. All right. So now we are looking for the final volume, right? So we have our combined gas law right here. Now we notice in this equation, right, this problem, there's nothing constant, right? So we have to use everything. So we are looking for V2, and we have to use all the factors. So simply the first thing you're going to do is cross multiply. So you'll get P1 V1 times T1. You take the T2, you put it over here, equals to P2 V2 times T1. All right, we cross multiply. We figure out what we're looking for. We're looking for V2. So what we do, we take these other two guys right here, the P2 and the T1, and we divide both sides by them. So what happens when we divide both sides by P2 and T1? Let's see. We have P2 and T1 going there. We have P2 and T1 going there. What happens on this side? Okay. Our P2s will cancel. Our T1s will cancel. So what do we have now? We have this situation where P1, V1, and T2, okay, over P2, T1 equals to our V2. All right, so it's a bit jumbled right here, but V2 is equal to these guys on this side right here. This is our equation that we desire, and we just plug the values in. Okay, so you plug the values in. Now, for the sake of space, right, guys, I'm going to leave the units out, but I always want you to put units in, because when your units cancel, you know you did the problem properly. All right, so I'm going to put, for P1, I'm going to put 1.30. All right, for V1, I'm going to put 46.0. Okay, for T2, we got to be careful, it's T2 this time. It's going to be this guy over here, 275.09. Alrighty, I'm going to put a divisor right there. My P2 is 285. Alright, and what's my T1? My T1 is 278. Alright, so I put them in, 278. Now once again, you should use units. So when you do the calculation, alright, I should wind up with, let me see what I got. I got 20.8 mLs. Alright, so see if you got that. I got 20.8 mLs for this guy right here. Now notice in this problem, there are no variables which are constant, so we had to use everything. We didn't panic, we just cross multiplied and then isolated. Okay, moving on. Alright, we have this other guy right here which I kind of messed up on, but no problem. We're reading this problem. We have 0.05 liters of oxygen gas kept in the cylinder. Okay, so we're making our chart right here. So they give us a volume of oxygen gas. All right, so V1 is going to be 0.0500 liters. Okay, kept under pressure, right? And is going to fill a 4-liter reaction vessel. Okay, so our second volume is going to be 4 liters, all right, in which the pressure is 0.980 atmospheres. So they're telling you you're starting with this volume, you're going to a different volume and a different pressure of 0.980, right? Now you read on. The question says, what is the initial pressure of the gas, all right? So if they're trying to ask you to find initial pressure, obviously we're looking for P1. We don't know P1, and this is our P2. So 0.980 is P2. All right, notice in this problem, they did not mention temperature. So what you can do, you can assume temperature is constant. You change it to a 1, and we wind up with P1, V1, equals to P2, V2. Okay, so this is a Boyles Law equation at constant temperature. Alrighty, as we go from there, we're looking for the initial pressure, P1. So P1 is going to be equal to P2, V2 over V1. You plug your numbers in. Okay, our P2 is 0.980 ATMs, right? Okay, put a parentheses around that. Our V2 is 4.0 liters. I'm looking at my chart on this side right here. So I have P2 of 0.980. I have V2 of 4. divided by V1, which is 0.0500 liters. All right, I'm going to do my calculation. I did it already, so I'm looking at it. I got 78.4 atmospheres. Okay, now this is implication in terms of you've seen when you go to like a party store to get your balloons filled. They have in those containers gas under very, very high pressures. Normal atmospheric pressure for us is 1 atm. All right, okay, and in those containers they have a large amount of gas under pressure. Okay, so there we go. That's our answer for that guy. And moving on to the last one. All right, you're doing number 7. We have the Celsius temperature, okay, of a 3 liter. So we're gonna look of gas. So we're gonna write that down. Our V1 is 3.0 liters, right? Okay, it's lowered, so we're lowering our temperature. We're cooling it. Okay, it's going from 80 degrees. So 80 degrees is our starting temperature. So you write 80 degrees down. C. And to 30 degrees. So our T2 is 30 degrees. All right. What will be the resulting volume? So we don't know the final volume. Okay. Now in this problem, right, they said nothing about pressure, right? So pressure is constant. So we have P1 V1 over T1 equals to P2 V2 over T2, right? Pressure is constant, so we can basically cancel it out, right? So we don't need it. Now we are looking for V2. All right, so what we do, we're going to cross multiply. Okay, we're going to say this T2 goes over here, this T1 goes over here. All right, so what's going to happen is we'll have V1 T2 equals to V2 T1, and we want to find V2. Okay, so we're almost there. All right, so to find V2, what do? Divide both sides by T1. So what's going to happen is our T, we will wind up with V1 T2 over T1 equals to V2. All right, now before we do anything else, folks, what we have to do in terms of our temperatures, we got to convert them to, convert them to Kelvin. All right, so what we're going to do, we're going to add 273 to both of these guys. All right, never forget that. If you're working with degree C, please convert to Kelvin. Okay, at 80 degrees C, we're looking at 353 Kelvin. All right, 353 Kelvin. And at 30 degrees, we're looking at 303 Kelvin. Okay, so our T2 is 303, our T1 is 353. We plug them into this equation right here to find V2. So we go from here. We got V1 right here. All right, let me use a different color. All right, our V1 is 3 liters. All right, 3.00 liters. All right, parentheses. Our T2, looking at carefully, is 303. Okay, our T2 is 303 Kelvin. It makes sense because we dropped the temperature, we cooled it. And last but not least, our T1 is 353 Kelvin. Okay, we see that our kelvins are able to cancel, and we're left with liters, so it makes sense. All right, so I'm going to go to my calculator, go to my on button right here. All right, so I'm going to put 3.00 times 303. Okay, enter. That's give me 909 divided by 353. Enter. I got 2.58 approximately, 2.57, 2.58. So 2.58. Okay, liters is my answer. Okay, and I asked myself, does the answer make sense? I lowered my temperature, and temperature and volume have a direct and proportional relationship. So I do expect my volume to get lower. It was originally 3. It went to 2.58, which is a lower value. That makes sense. Okay, and that's it. All right, guys. As always, hard work and sacrifice equals success. I hope this video is a help. These calculations are not that bad. Okay, start with your combined gas law. If something is constant, you turn it into 1. Remember to cross multiply and isolate what you need. Remember always to use Kelvin temperature and go from there. All right. Hard work plus sacrifice make little success. Again, see you guys later. Take care.